We have discussed the W bar matrix. Now let us discuss the W matrix. The W matrix is also called the DTFT matrix, and different to the W bar matrix, it is complex phases that is rotating clockwise. You realize that in the last perspective, the phases are rotating anti-clockwise. The W matrix actually is rotating clockwise. So that is the only key difference between the W bar and the W matrix. Other than that, both W bar and W matrix are square, n by n. And in different books, this constant 1 over n is sometimes placed in W bar and sometimes placed in W. So there's a lot of confusion here. But let's continue with our notation in the analysis, where we are saying C is equals to 1 over n times W of x. Then this 1 over n is 1 over n times W here, and this W is actually represented within these elements of small w by the power some integer, and you realize that this integer also reveals how fast is it rotating. Here W0, the whole columns are W0, therefore you realize that this does not change. W0, W1, W2, it is changing by where this W is this complex exponential here, and in this example you see that it is rotating by pi over 4, and because of this negative sign it is rotating clockwise. So W0 to W1 is rotating clockwise by 45 degrees. W1 to W2 also rotating clockwise by 45 degrees. This column W0, which will start off with here, W2 means that it will move by 90 degrees because it's 2 times 45 degrees. So now you understand that here this notation here, the omega is radian per sample. How many radian is it moving at every sample? And because we are talking about 2 pi over 8, every sample we are rotating by pi over 4 radian. But of course in this column we are moving 2 times faster, in this column we are moving 3 times faster, and so on. Right, so to summarize, as the columns are going from 0 to column 1 to column 2, the complex phasor is rotating faster and faster. However, if something very interesting happened at the last column, you will realize that this complex phasor can also be viewed as a phasor that is rotating anti-clockwise at pi over 4. So this phasor, compared to this phasor, they are rotating at the same speed but just different direction. The other way to look at it is this first column is not rotating at all, it's constant. This guy is rotating 1 round in n sample, this guy is rotating 2 rounds in n sample, therefore the third guy is rotating 3 rounds at n sample, 4 rounds at n sample, 5 rounds, 6 rounds, and 7 rounds. So you get the picture that when you're rotating 7 rounds at n samples, this is actually visualize it as rotating clockwise versus anti-clockwise at n samples, 1 round. And this diagram is not only here, in fact if you look at the previous diagram, it is also the same. You compare this as well as this. This is rotating anti-clockwise of the n sample, 1 round, and this is rotating clockwise 1 round of the n samples. So it will take a while for you to absorb this insight, but bear with this, and then later on you can interpret what happened when we go from B0 to B1 to B7, followed by B8, B9, and so on and so forth. Okay, with that, let's summarize the DTFS from a linear algebra perspective. The synthesis equation says that X is equals to W bar C, where W bar is the inverse of 1 over n W, and C is the analysis equation is 1 over n W X. Most books will show you the W matrix on the DF, or W is the DFT matrix. To get W bar from 1 over n W, you use an operator in the linear algebra, called the Hermitian operator, which is the complex transpose. You might not need to do it in this course, but this Hermitian transpose is the operator that introduces the negative to the positive between the W and the W bar, changes the sign of the complex exponential. And that's it. So maybe I would suggest you go to this EPFL course for this link to visualize what does omega means, how does omega can be interpreted as a change of angle of a complex rotating phasor when we go from sample 0 to sample 1 to sample 2 and so on. Thank you.